All right, it is the time to start. I want to point a couple things out on Carmen before we get into our slides. So one, just as like my workflow, what I'll do, because I will always, only one time have I ever finished early in a lecture. I always have excess material. And so what I do is when I finish, I go grab all the slides that I didn't get to and I put them into my next slide deck. So what we didn't get to on Thursday is what we're going to start with today, so you don't need to go back to that old slide deck. Whatever I have in today's lecture module is where you should be starting. You guys all had recitation on Friday. I now have in the additional lecture resources my key for that first recitation assignment. Go back and cross-check with that. If you need it earlier, I tend to post it on Mondays, but if you're somebody that's like, I really want to see this now, contact me. We can figure something out. Maybe I could even figure out how to have it release after you submit it. That sounds like advanced Carmen things that are beyond me, but I'll figure it out. So if that's you, just let me know. We can figure it out. So much figuring out happening. All right. The other thing I wanted to point out is that after each lecture, I have 3-ish, so 2 to 4 exam-style questions that I think you should be able to answer after this lecture. I had put those into my lecture page. I pulled them out and put them into the module itself just because I want you to try those so that once you get to the practice exam, that's not the first time you're trying questions, okay? I would also keep in mind that you have 50 minutes to cover 20 questions on the exam, so be aware of how much time you're taking on those. That is a good time to practice. Can I answer questions quickly? There are answer videos embedded in those quizzes, so if you get done and you're like, I don't know why I got that wrong, you can watch a little video of my explanation. Any questions? Logistics? We're all happy to be back after the long weekend? Okay. Then, let's get into content. We are going to start with my usual approach, is that I want you to try and remember what we talked about the last time we met. So, try and fill in the blanks for these. Pick the right word. How do we describe mixing, the mixing process? And how are we defining these different delta H's, which are enthalpies? Once you get through that, there's another jog your memory on the next slide. Feel free to chat with the people around you or do it yourself and compare answers. But if you want, this is a good time to get the chatter out of you because we have some lecture to do after that. All right, let's do thumbs up for the first option and thumbs down for the second. The entropy of a system almost always, how you do thumbs up if you say increases, thumbs down if you think decreases. Yes, it almost always increases. Our caveat, our exception is coming today. But when we put a solid into a liquid and we mix it up, or a liquid into a liquid and mix it up, we are increasing the disorder. And so we're going to have an increase in entropy. That is almost always, that increase encourages or discourages the mixing process. Does entropy encourage or discourage mixing? See, like less of an engagement on this one. It encourages. When we want entropy to increase, our whole universe tends towards disorder. We really like to disperse the energy. We will get into that in chapter 19, but this is like the key two things that you need to know about entropy right now. All right, delta H, solute and solvent are always positive or negative. Which one is it? Good, that's positive. Remember that these are our like AAs if we were gonna mix B and A. If we're going to mix A and B and we want them to interact, we need to pull A apart from itself. We need to pull B apart from itself. That means that that's an endothermic process. We have to put energy in to make that happen, which kind of leads into the second statement here, because we are breaking intermolecular forces. Okay, we're going to take these A's that like to spend time next to each other. We're going to pull them apart. That requires some energy because we're breaking their interactions. All right? The opposite is true for delta H mix. That's what we get out of this process, right? We get to bring A and B together. That means that it's a negative process. Okay, this is forming the A and B interactions. All right? And we are making new interactions. So this is exothermic, right? And the question of whether or not the whole process is endo or exothermic is a balance between 2 and 3, right? Those 3 delta H's, which comes together in this when delta H of the solution, so that's the sum of those 3 delta H's that we just talked about. When the sum is positive, the mixing process is endothermic or exothermic. Good. That's endothermic, which means that we need a little bit of energy to drive this thing forward, which is going to come from the thermal energy of our solution. So that means it's going to feel cold. All right? Next one. Now let's look at some actual molecules. Okay, so which molecule would you guess is the most soluble in water? So take a minute by yourself to look at these. I'm going to ask you at the end of that minute to hold up a 1, 2, 3, or 4. I think I have a semi-hint there. I want you to maximize delta H mix. Which of these molecules will have the strongest intermolecular forces with water? That's going to be the one that's most likely to mix. Okay. All right, in 3, 2, 1, what's your answer? All right, good. I am seeing lots of 3s. I would have gone with 3. I am sorry, I'm taking some things for granted here. I use the organic shorthand, these squiggles. Each one of those points is a carbon, and then it's saturated with hydrogen. That's something you'll learn in organic. On the exam, I would expect us to either give you that whole image, right, like the one in 1 for hexane, and that condensed formula. So you'll see what's like that it's C6H14O2, all right? I picked 3 because I am looking for the molecule that will have the most and the strongest interactions with water. What I notice about this 1,6-hexanediol is that it has an OH, an alcohol, on both ends. All right, so both ends can hydrogen bond with water. That's important, okay? And that's in contrast. We eliminated hexane immediately. It's nonpolar entirely. Hexane can't offer any strong interactions with water. 2 and 4 are, valid options to consider, right? Because they both have, well, this one has an OH, so that's hydrogen bonding, right? This one has a fluorine, so it definitely has a dipole. And it's got lone pairs that could hydrogen bond with water, but each of those only have the one spot. The fact that 3 are diol, which is the double alcohol, has it on both ends is what's going to make that the best choice for this question. Okay? Does that make sense? Okay, you're looking, especially since these are both non-polar tails here, those are not going to play nice with water. All right? Okay. Let's dive back in. I want to return to this graph real quick. So I didn't say this on Thursday, and I should have. Maybe you guys got to this on your recitation, because I did ask you about this graph. But I just want to say, if you are underneath one of the lines, that is an unsaturated solution. Okay? So let's take, we'll go with potassium chloride. I'll draw in blue here. I'm going to follow this, right? If I am underneath the line, but not including the line, that's unsaturated. I have yet to hit the point of saturation. I could still add more solid and see it dissolve, okay? Once I am at the line is this special tipping point, right? Where I am saturated. The solution is saturated at the line, but I don't see any solid because I have just saturated it. So there's no solid sitting at the bottom, right? But it is saturated. Any more that I add would just sink to the bottom and be solid, okay? That's at the line. Anything above the line, that's saturated, and I will also see some solids sitting at the bottom that I can't dissolve because I've already went past saturation. All right? Does that feel comfy? We're all getting good with this graph? It's very likely to come up on your exam. All right, so those are the 3. But there's unsaturated, there's saturated, but you don't see any solid, and then there's saturated, and you will see solid. I did finally find the simulation that I wanted. And I'm going to show it to you, maybe if it loads. Okay, so we're going to do a slightly soluble salt. I think I picked copper iodide. So I'm going to go in and I'm going to shake my salt shaker. All right, and so what we see is that all of the solid has dissolved. All right, and so we can see that up here in our dissolved versus bound. None are bound. Once I start having bound, that means I've got solid sitting at the bottom. All right, so all of them have dissolved. Okay, I'm going to guess this is unsaturated at this point, right? Because I can add another shake, and I still don't have any bound. I only have ion, so it's all dissolved. But of course, as I keep adding, I'm going to get to a point where I can't do that anymore, right? I think it's that, there we go. All right, we just hit it. All right, now I have bound, right? And you see those numbers are changing. Again, that's reflective of the fact that this is a dynamic system. I have some that are in solution that come and they bind, right? And we have some solid. And then those leave, and they come back, and they leave, and they come back. But on average, we have 63 dissolved, and we have about 8 units that are bound, right? And no matter how much I keep adding, if I don't put in more water, I am never going to dissolve any more. So that number, that's our solubility right there. We've hit the saturation at like 63, 65. Obvious, it's changing a little bit, but I'm never going to get past that unless I do something to the system, like add more water or turn up the temperature on it. Okay? Does that make sense? Okay. That's the visual that I want you guys to have, that it's not static. They're not destined to be a solid or a dissolved ion. They're constantly changing. All right. We have one more definition for a solution, and that's supersaturation. All right? So a supersaturated solution is one where there's more solute dissolved than should be physically possible. All right? And you don't happen upon these accidentally. I'm going to point out the way that we read this graph, supersaturation is represented on this graph. All right, so let's go back to our potassium chloride. Let's say we're at 60 degrees. If I add 80 grams, I would expect that I would dissolve 45 grams. And then here, that excess, this is just solid sitting at the bottom. Right? I haven't done anything special to get that extra large amount of solid into solution. Okay, so that's not supersaturation. Supersaturation, all right, we'll look on the next slide here. I have an example. All right, so you will make a supersaturated solution by heating. So you're going to heat up your solution and saturate. Okay, so let's say we go up to like 80 degrees Celsius, and I can dissolve a bunch of salt at that higher temperature. And then I'm going to let that sit and slowly cool down and not mess with it. And for some salts, not for all, but for some, as the solution cools, the salt, we call it the excess, and we will spell excess correctly, doesn't drop out. In other words, it stays in solution, okay? Even though at that lower temperature, it shouldn't be possible to dissolve all that solid in that amount of liquid at that temperature, all right? It's called a metastable solution. So somehow we've just like, we've trapped, through careful work in the lab, we've trapped it up here, okay? So this is our metastable solution, and that's supersaturated. All right, the thing is that there is a little blip, okay? It's stable there, but if I nudge the system a little bit, say by adding a seed crystal, as you see in this picture, so here's our supersaturated solution. Okay, and then I add a seed crystal, and everything comes crashing out because that little seed crystal prompts us over to drop all the way down here. So here's our stable, saturated solution. Okay. Again, this is not, so if the answer is something about supersaturation, we will likely tell you that we prepared the solution very carefully by heating it up and then slowly cooling it down. Okay, and then with a little nudge, we will get it from that supersaturated over to a stable saturated solution, and that process is exothermic. All right, so we can watch a little video here, which means that as we go from here down to here, we're going to see heat evolve. Okay. Let's see if this is program.
This is a supersaturated solution of sodium acetate. Supersaturated means it's beyond saturated. It's holding more solute than it should be able to. If we add just a little bit of solid sodium acetate, we can make everything crash out of solution. What you can't see on this video, but you may be able to see here, this reaction is very exothermic. It's really, really hot. It's so hot it's starting to turn some of the water vapor inside to steam.
All right, so again, you don't just it's unlikely that you will accidentally make a supersaturated solution, okay? And we're gonna have to tell you, hey, we did this. Otherwise, assume that we're dealing with a saturated or unsaturated solution. All right, any questions on salts in solutions before we pivot? All right, we're pivoting. We're going to talk about gases now, all right? So instead of a solid solute or a liquid solute, for that matter, we are going to talk about gases, all right? Gases also dissolve into liquid. All right, so now that means when we talk about the solubility, we have to, one, consider what is the solvent, same as we did before. We need to know what the temperature is, but now we add another variable. We need to know the pressure, the partial pressure of the gas, all right? So obviously that's not relevant for a solid or a liquid, but it is now another variable we should consider. All right, so we've got 4 gases here. Their molar masses and then the solubility. And I've plotted those against each other, and we see a general trend that as the molar mass increases, our solubility increases as well. All right, so we can say there's a trend there. All right, so why might that be? So this is N2 down here, and up here we've got our krypton. All right, so basically the bigger the gas molecule, what intermolecular force is increasing? Dispersion, right? So those larger gas molecules are going to have stronger intermolecular forces with water, which means that they're more likely to dissolve in water, right? So that trend that we're seeing there is just that as the molecule gets bigger or as the atom gets bigger, or atom gets bigger, stronger dispersion forces. Which increases the solubility. All right, so bigger the molecule, just like very similar to what we talked about. If it's going to have better interactions or stronger interactions with water, in this case our solvent, then we would expect more to dissolve in there. All right, we're going to draw a relationship between our partial pressure and our solubility. Again, only relevant for gases. Okay, so we're looking at the effect of increasing the pressure here. So we've got our little piston sitting above our water. Let's say it's water. All right, and we're looking at CO2, and then we push the piston down, thus increasing the pressure above that solution. We're going to force more of those CO2 molecules into solution. All right, so as the partial pressure increases, the solubility increases, and it's in a nice, easy, linear relationship. So that's our partial pressure on the x-axis. As that goes up, our solubility increases, okay? This is, again, a lovely, simple equation. This is Henry's law that explains this relationship S sub G, that is our solubility, which for us in this graph is in millimolar, which we'll talk about later, but basically moles per liter of solution. And that's moles of gas. Okay, so how much can we put in there? K, this is Henry's law constant. And it's just specific to our gas molecule. It's also the slope of our line. All right? And then that's our partial pressure of the gas. Okay? So if you've ever used one of the soda streams and you carbonate your own water at home, what's happening is you're basically increasing it. You've got a tank of CO2 on the backside, and you press the button, and it raises the pressure of CO2 above that water, thus forcing more CO2 to dissolve in the water, right? And then when you open the cap, then that pressure drops because all that CO2 is going out, and you see some of it fizz out of your liquid. Okay. All right, so which gas would you expect to have the larger Henry's law constant? The top part there of the slide is what we've just said. Would I expect K to be bigger for Cl2 or H2? Okay, so let's do 1 for Cl2 and 2 for H2. So which one should have a larger K? If you want, take a second, chat with the person next to you. And if you're feeling up to it, you could even try and place those two gases on our graph. Right? Again, what am I thinking about here? How strong are the interactions between these two molecules and water? All right, what are we thinking? Is it 1 or 2? Who has a bigger K value? Good. 1, Cl2, it's a much bigger molecule. In fact, it's bigger than any of the other ones we have on this graph, so I would guess that it probably shows up here. Right, it's bigger than O2. And H2 is about the same size as our helium down here, so maybe H2 is trending right along there. All right, so that means a big K. Right? It's going to have, at the same partial pressure, I am going to dissolve a lot more Cl2 and H2 into water, and we can chalk that up to the fact that Cl2 has stronger dispersion forces. All right, so that's our relationship between pressure and solubility for a gas. And now, we're going to, instead of looking at changing pressure, we're going to change temperature. All right? And this is where our caveat comes in, all right? So I think most people felt really comfortable with the idea that when you increase the temperature of water and you're trying to dissolve a salt, you're going to get more salt in that solution, right? So that meant that temperature increased the solubility of a salt. Based on this graph, where we're looking at the solubility of gases versus temperature, you see that the opposite is true. As you heat up a liquid-gas mixture, your solubility of the gas drops. Okay? So the opposite. Increasing temperature decreases the solubility of a gas in liquid. All right? So this is that entropy exception. So when we dissolve salt, I talked about this, when we dissolve a salt into water, that often increases our entropy because the salt was in that perfect little lattice, right? And then when it dissolves, those ions can be anywhere, right? So you're giving them more disorder, more freedom. However, the opposite is true here. When I take a gas and I have it confined to the liquid phase, by taking it out of the liquid phase and into the gas phase, that increases my entropy, right? So increasing the temperature is going to actually not favor mixing, right? Entropy, in this case, favors that gas leaving the condensed phase, right? So entropy in this case doesn't favor mixing. It favors getting that gas out of there into the big world where it can go anywhere it wants, all right? So I will say you guys probably, well, I notice it because I think about it a lot, but when you go to boil water for pasta or whatever you're making, before the water boils, if you pay attention, you will see some bubbles before it boils, okay? Has anyone ever noticed this before? Right? You're like, oh, yay, it's boiling. And then you're like, actually, it's not. That was just the gas that was dissolved in the water leaving, okay? So you're seeing this happen. You're seeing the temperature increase, prompting that gas to leave, which means that the solubility is decreasing, all right? All right, I think that's all I have to say about this. Any questions on that? Cool. I think we're ready to jump into 13.4 then. All right. So we've talked a lot about solubility and saturation, and now we have to do some like quantitative work behind it. All right. We need to be able to express to people the solution concentration. And I have been sort of like tacitly saying these units without defining them, and now we define them. All right. First, we have qualitative descriptions, just so that we're all on the same page. I could describe something as being dilute. That just means that there's a low concentration. And like a alarming amount of creativity, a concentrated solution has a high concentration of the solute. All right, so those would be like our two qualitative descriptors. And then we have a ton of quantitative descriptors, and these are just some of them. These are the ones that you are expected to know for your exam, and they are not on the equation sheet, okay? So when I tell you, hey, calculate the molarity, I expect that you know what molarity is, okay? Obviously, we're going to go through these. This is not all, I will talk too much about all of these, all right? Main point in these quantitative descriptors, we are going to take the amount of solute, usually the solute. We could do it from the solvent's perspective. But the amount of solute, that could be moles, mils, grams, okay? And then we divide it by the total amount of stuff. Okay, or solvent. And again, I could express that amount in moles, mils, grams, right? So volume, amount, mass. Again, this is why we have so many different ways of expressing concentration, because I could do it with any combination of these units. All right, we'll go over the most common expressions, the ones that we have listed there, and that I expect you to know. All right, but generally, we say, how much solute do you have? How much solution do you have? And then you divide those two. All right, so let's start off with mass percentage. All right, here's your definition of mass percentage. It's the mass of our solute divided by the total mass of the solution, and then you multiply by 100%. So for example, I was trying to find something that you regularly encounter. If you go buy bleach from the store, bleach will say it's 7.4% sodium hypochlorite by mass. All right? Then the question is, what does that mean? How can we break that down? Well, that must mean that for every 100 grams of solution, 7.4 grams were that sodium hypochlorite. Okay? Then I'd multiply by 100% to get that 7.4%. Right? So that's how I would read that. I would say, well, take that percentage and break it down into, like, if I had 100 grams, I must have had 7.4 grams of NaOCl in there. And I think I pulled these problems, or they might still be practiced on Pearson. We also have, instead of by mass percent, you could do volume percent, which would just be volume of the solute divided by volume of the solution. That's how most, like, alcoholic beverages are sold. So like ABV is alcohol by volume. That's what that means. All right, so that's what you would read this as, okay? Oh, I do want to point out, if this were a two-component solution, where the other component were water, we know we have 100 grams minus 7.4 grams of water. Okay. So you can sneak some other information out of that, which will be useful later on when we have to convert between different concentration units. Okay. Okay, so that's mass percentage. All right, and we have two very similar units, ppb and ppm. All right, they are, again, very, very similar to mass percentage, but now they are for very, very dilute solutions where it doesn't make sense to talk about mass percentage because it's just so dilute. All right, so ppm is, again, mass of the solute divided by total mass of the solution, but instead of multiplying by 100%, we're going to multiply by 10 to the 6 or a million. Right, so that's our ppm, parts per million. So, for example, that would mean one ppm would be 1 gram of solute per 10 to the 6th grams of solution. Okay, so for every million grams, one of them is your solute. Okay. And then for ppb, the same thing is true, except for that now it's 1 gram for every billion grams of solution, right? 10 to the 9th. So let's consider the EPA limit on arsenic is 10 ppb. All right. What's the gram limit of arsenic in 1,000 grams of solution? Let's say drinking water. All right. So then we could go through and solve out for, well, how much can we have in there and still meet the EPA's guidelines? Side note, the EPA also acknowledges that no amount of arsenic is healthy. But this is our guideline. All right? So we'd say, all right, well, we're looking for 10 ppb. Okay, we know that's our limit. We're looking for the mass of solute. Okay, that's our arsenic here. Okay, so we're going to look for grams. And we're asking for it about 1,000 grams of solution. Okay. And then to finish out, right, I still have my 10 to the 9th because I'm dealing with ppb. Okay, so I'm going to divide by both sides by 10 to the 9th, multiply by 1,000, because I want to isolate that x, right? So I'm going to find that x is equal to 0.00001 gram of arsenic. In other words, I can have 0.01 milligrams of arsenic for every 1,000 grams of solution. Okay. So a very small amount. So it makes sense if you're going to work in ppm and ppb, again, it makes sense to do it with really dilute things that we don't want very much of. So this is really common for drinking water guidelines because we want very low concentrations of arsenic, lead, mercury, all those heavy metals that we don't want in our drinking water. All right, so that's ppb and ppm. Now we've got mole fraction. So instead of dealing with this on a mass basis, we're going to do it by moles. All right, so literally number of particles, and we're going to use this a lot in section 13.5. All right, so I could just say, again, and this is same concept, the amount of stuff, right, that we're interested in, so moles of the solute divided by total moles of solution. All right, and that total moles of solution is going to be the sum of our solvent plus solute if it's a two-component system. Note that we are dealing with a fraction, so this needs to be between 0 and 1. All right, our percentages, we're going to be between 0 and 100%. And when you sum all your mole fractions, you better get 1, otherwise you have lost something, right, in your solution. You don't want to lose anything, and you don't want to create anything that shouldn't be created. All right? So I could just say if I had 10 moles of ethanol plus, what did I do here, 50 moles of H2O, I could ask you what the mole fraction is. Side note, if you're unfamiliar, that's chi, our Greek letter. So when I say what is chi, I'm asking for the mole fraction. So if I ask for the mole fraction of ethanol, I'm going to take the moles of ethanol divided by the total, so 10 plus 50, right? And so that would be 0.167, right? I could think about that as a percentage, a mole percentage if I wanted to. So that's if I put my hand in and I were to grab, like at random, one molecule, I'd have a 16.7% chance of grabbing ethanol instead of water, okay? I could go through and do the same calculation for water, or I could just say I know that since this is a two-component system, chi H2O equals 1 minus chi ethanol. So that's going to be 1 minus 0.167. And so this is about 0.833. Okay. Again, that's where we get the point where, like, hey, your two chi's better equal 1. Otherwise, you've lost something or created it out of nothing. And you don't want to do either. All right. So this one will come up. We're going to have to calculate it for some other problems. All right. All right. Last two, molarity and molality. I don't know why we had to choose such similar words, but I wasn't there at the table when they made the decision. Capital M is for molarity. That's moles of the solute divided by liters of the solution. All right, I'm going to highlight this because I think it's probably going to be one of the more common mistakes, remember, of solution. All right, molality, little m, that's also moles of the solute on the top. And then it's kilograms, the mass of the solvent, not of the solution, just of the solvent. Okay? So be aware that those are two different denominators, all right? It's not just the mass of the solution, it's the mass of the solvent. Okay, and so this seems like a good time to say, like, why would one bother with having both of these units? They're really similar. The answer is molarity this is what we're going to work with mostly. I would say when you go into a chemistry lab, I would expect to see most things written in molarity. But if you were doing an experiment over a huge temperature range, okay, so if you're getting things really cold or getting things really hot, going like across that spectrum, you're going to run into a problem because volume changes with temperature. So if you were going to change the temperature on a solution, your molarity changes with temperature. Okay? That could be problematic, right? If you're you want to have this number in your calculation, it's problematic if you're going to see a change based on the temperature. All right? That's not true of molality, because our kilograms of solvent do not change, because mass is mass, Volume, on the other hand, is a function of temperature. All right, that's my little pitch for why on earth would we have two such similar expressions. So let's do some practice. I'm going to go, there are two types of questions, all right, that you might get on these. Say two types. A lot of this is going to be embedded in other questions, okay? Did I move forward too fast? Are you still writing that down? Okay. When we get into section 13.5, which I'm hoping we'll do today, we're going to need to calculate these concentrations, so they might be embedded in other parts of questions. On the exam, I would expect you to see at least one question where it's like, hey, do one of these two calculations. Either tell me what the concentration is in these units, or convert between units. All right? I guess all of that is to say that being able to do these concentration calculations is really important, not just for one question, but for many, because it like weasels its way into lots of different questions. So don't sleep on this one, all right? So let's do a practice problem. This is the most straightforward, all right? I give you a way, I describe prepping a solution, all right? And then I just ask you, what is the what is the concentration in these units? All right, so I again made this a very straightforward problem. I say I have 106 grams of sodium carbonate. I'm going to add it to 2 kilograms of water. What's the molality? All right, so for this, I would just grab my definition of molality and say for that, if I want to calculate this, I need to know moles of solute, and I need to know kilograms of solvent. And this question is very kind in that it presents that information pretty much like readily. I just need to convert grams into moles. All right, and there's our formula weight right there. And I was feeling extra nice that day, and I just made it 1 mole. All right, so I have 1 mole of solute. I won't be specific what I'm talking about. 2 kilograms. Oh, and I guess that we should have some extra sig figs, one of my least favorite subjects. All right, so that tells us that we have 0.500 molality. Okay, that's the most straightforward question. Here's how I prepped this. Tell me the concentration. I think the problem that will be that's more complicated, which I have on the next slide. People are still getting this in. Okay, the more challenging question, something like this, okay? And I highlighted those because as I was looking at this later, I was like, oh, I should have included this information for you, but calculate the molarity of lead in a 9 ppb aqueous solution. And we're going to assume that the density is 1 gram per mil. And so now it's not about the preparation. It's saying, hey, take ppb and convert it to molarity. All right, so this is an inherently slightly different question, and I'll show you my approach to it. When I get questions like these, I start out by asking myself, like, what does ppb mean, right? So ppb means grams of solute. In this case, it's going to be lead, divided by grams of solution, times 10 to the 9th, right? That's our definition. So if I had a 9 ppb solution, okay, that would mean, and this is the part that I think is a struggle, but I get to decide. I get to make up whatever solution I have. I'd have no amounts here. I am just going to say for ease that means that I have 9 grams of lead for every 10 to the 9th grams of solution. That might not seem like a big jump right now, but that's the place that I would begin. I'm going to actually put some real numbers to this and say, well, if I had 10 to the 9th grams of solution, that would mean I have 9 grams of lead in that. All right? So I'm going to translate it into a real solution. And then I'm going to say, well, what do I need if I'm going to calculate molarity? This is what I know about my solution. This is what's given to me. How do I take that information and turn it into the units I need for molarity? Okay, so for molarity, I'm going to write that out. What do I need to know for molarity? I need moles of lead, and I need liters of solution. And I see my roadmap right away, right? I know that in this solution, I've got 9 grams of lead. I can convert that to moles, right? I've got my grams per mole right up there. That's a simple conversion. So let's do that. I can get moles of lead. 9 grams of lead. All right. And we're seeing it's 207.2 grams per mole. So that translates to 0.0434 moles of lead. All right? And now this other piece here. I need to know the liters of solution. All right? Well, I'm told that I know the density, that every gram of solution is a milliliter. So I can take grams, right, my 10 to the 9th grams, and I can bring it to liters. Okay? So say 10 to the 9th grams. All right, I'm going to take that to mils first. Okay? So this is, again, trivial math. But if you don't have 1 gram per mil, which is our density of water, what we're usually going to assume, then this is non-trivial, so don't skip it. Okay, so for every gram, I have 1 mil, and I don't need mils, I need liters. So I'm going to take this final conversion, right? And I'm going through, I'm keeping my units because that's what good chemistry looks like. And I say, I have 10 to the 6th liters. And now I have both of the things that I need to calculate molarity, right? I've got moles and I've got liters, right? So here and here, these are the 2 things I needed to calculate molarity. So molarity, M equals 0.0434 moles divided by 10 to the 6th liters. This 9 ppb solution is 4.34 times 10 to the negative 8th molarity. And again, a pitch for why we use ppb, because no one wants to say 4.34 times 10 to the negative 8th molarity, right? That's a big mouthful. All right, so this is the structure. Write down what do you know from the given concentration units? What do you need to know for the new concentration units? And then get your roadmap from how do you go from one to the other. And of course, now you all have a chance to practice. All right, so now here is your practice problem. Okay, so go to the next slide. I'm going to leave this up in case some people are still writing, but start working on that next one where you are converting between a percent mass and molality. All right, guys, let's look at this together. Okay, so here's the thing. All right, we've got our concentrated HCl, and this actually is in lab often written as 36% HCl. All right, really strong acid, you don't want to mess with it. Okay, so I want to get that to molality. If I'm going to calculate molality, I need moles of HCl divided by kilograms of solvent, which we know is H2O because I told you that this was aqueous, right? So aqueous there tells you that this is H2O, and I haven't told you about anything else, so we can assume that this is just HCl and H2O, all right? So I need to find moles of HCl, and I need kilograms of water, right? That's what I'm aiming for. What do I get from 36% HCl? This is the part that I think stumps people. How do you use that to make a movement forward? I make up a solution. I say I have, and I'm going to use 100 grams because it makes math easier. I say in 100 grams of this solution, how many grams would be HCl? 36, right? That would give me a mass percent of 36. So now I have concrete numbers to work with that are units. That's 36 grams of HCl for every 100 grams of solution. And so now I'm going to work with those numbers to get myself over to those units. So I can say 36 grams of HCl, right? I want to know what that is in moles. So that's going to be a little less than 1. It's 0.987, right? That's what's going to go in here, all right? And then I say, all right, well, I've got that. So we did half of it. We're halfway there. Now I need to know kilograms of water. And you're like, oh, she didn't tell us how much water was in there. But we know, right? Because it's only 2 components. So if 36 grams of that 100 were HCl, that must mean that 64 grams were water. Right? We all following? Yeah.
How do you know you have 100 grams of solution?
I just decided that I was going to use 100 grams because that makes it the math easier. You could have done 200, right? The concentration is always going to be the same.
I get that. Like, I just don't understand why. Like, I get the 36% of 100 would just be 36, but why can you do that when you're trying to figure out, like, the exact molality of, like, this solution, or is it all?
Right, so that percent mass. So focus on this for just a second, guys. So it doesn't matter if I am talking about, the thing about concentration is that it is the same if I am talking about this much, or if I have the whole room filled with 36% HCl, right? The ratio between the two is always the same, right? It's intensive. It doesn't matter how much I have of the stuff. The concentration is always going to be the same. So if I had 100 grams, I'd have 36, right? If I had 50 grams of my solution, I would have only had 18 grams of HCl. Doesn't matter how much you have. It just matters that you have the ratio correct. Is that sinking in? Does that feel comfy? Okay? Well, don't worry, you'll have lots of practice, okay, if this still doesn't feel good. So 64 grams, all right? That's what I have of water, and I am 1 step away from getting what I need. 64 grams of water is 0.064 kilograms of water, all right? So now I have everything I need for molality. That's 0.987 moles of HCl divided by 0.064 kilograms of water. That gives me 15.4 molal. And you'll notice that I was kind of sneaky. I included density, but you didn't need density. And that might happen on the exam, where we give you excess information and you have to make the bold decision that you're not going to use it. Okay? You would need that density if you were going to calculate the molarity, but you don't need it for the molality. Okay? All right. Just give me put your hand up if on Thursday you want to start with one of these problems. Does this feel, okay, great. All right. I felt that. We'll start with one of these. Okay. So put a pin in this. I will provide more resources for doing this and talk through more practice problems, but I want to move on into our colligative properties. Okay? So if this is a struggle, I will provide more resources and look for those on Carmen. All right? Okay, so we've got, like 15 minutes. All right? So I know it's hard to sit in an 80-minute lecture, but bear with me here, okay? Just take like 10 seconds to like tighten up your brain. Just totally a phrase that people use. All right, colligative properties. This is a real U-turn because for the whole opening of chapter 13, we were like, you have to think about the intermolecular forces. That's what matters to decide if it mixes. And now we're like, psych, don't even think about them, okay? Colligative properties are special properties that don't depend on the identity of our solute and solvent. All that matters is the number of solute particles, okay? That's the thing that matters, okay? When we go to calculate vapor pressure lowering, these are the 4 colligative properties we'll consider, okay? So when we go to calculate these, it doesn't matter what the intermolecular forces are. We spent all that time, and now we're not going to talk about them in 13.5. We're just going to say, how much did you add? Okay? So we're going to start here with vapor pressure lowering. And we're going to say, if you need a refresher on vapor pressure, that's from chapter 11.5. Okay, so we'll define it. Vapor pressure is the pressure exerted by the vapor when it is in equilibrium with the liquid. All right, so I think I've got a picture here. So we're going to have a new definition, maybe, volatile. Okay, a volatile solvent is something that exerts a measurable pressure, right? So I put ethanol into a capped vial. I am going to build up pressure above that liquid in that headspace, okay? There's going to be a measurable pressure, okay? So let's say I'm going to sit here. I've got like a little pressure gauge on top or maybe on the side here. Here's my pressure gauge, and maybe it's reading 50 torr. There's a measure. I can measure it, right? So that's in contrast to non-volatile. If something is non-volatile, not very many of those particles go up into the gas phase, so they don't exert a pressure, okay? So we've got our pure solvent here. It's in equilibrium, so it's established some pressure. In this picture, I've written it as 50 torr. And then I go and I mess everything up, and I dissolve a solute in there. Importantly, this solute is non-volatile. Okay, so notice that there are no red particles ever in the headspace or in the vapor phase up here. Okay, they only stay in the liquid phase. But they have an impact on the vapor phase. As I add these in, okay, as I add my red non-volatile solute particles into the solution, my vapor pressure drops. Okay, you add solute and the vapor pressure drops. Okay. So we're going to write this out. You will find that this class is oftentimes we're going to describe a phenomenon, and then we'll be like, well, let's write an equation for it. And that's what we're going to do now. All right, so we can describe this process using Raoult's law. Okay, so Raoult's law says that the pressure of the solution, all right, so that's with our solute and solvent, is equal to the mole fraction. All right, so remember we just learned that chi, that mole fraction. In this case, it's of the solvent, not the solute. I care about what percentage is solvent, times the vapor pressure of the pure solvent. Okay. And that is our mole fraction of solvent. Okay, by just considering this, hopefully it's obvious that our vapor pressure above the solution can never be greater than the vapor pressure of the pure solvent. Just mathematically, we know that chi has to be a number between 0 and 1. So P of the solution has to be less than P of the pure solvent. All right? So let's look at an example here. Calculate the vapor pressure in torr of a solution made by dissolving 10 moles of glucose into 90 moles of water. And then I tell you what the vapor pressure of pure water is at 37 degrees, which we can assume that's where we're working, and that's 47.1 torr. So I'll write this out. Here's our, we're going to use Raoult's law. So on the exam, you will get Raoult's law. That's on your equation sheet. And you'd read this and you see, oh, I've got a vapor pressure, and I'm adding a non-volatile in there. And so your mind should be like Raoult's law should be like flashing in big red letters in your brain. Okay, and we're doing water. And then this is just pure water vapor pressure. So I need chi. So chi is going to equal, and if I'm doing this from water's perspective, I want to use 90. So 90 moles of water, and I have 100 total. So it's just 0.9. So we'll have 0.90 times 47.1 torr. And that gives us, and I did actually have more sig figs in that case, but 42.4 torr. And that makes sense. Remember to do your reality checks. Is it a little bit lower? Yes, it is. That makes sense. Okay? So this is the most straightforward Raoult's law question that you will see. Okay. Raoult's law, okay, this thing that we just wrote up here, is what we use to describe an ideal solution. Okay? So in the same way that we used PV equals nRT to define an ideal gas, Raoult's law does the same thing for a liquid solution. All right? So an ideal solution follows, or let's actually say obeys, Raoult's law. All right? For that to be true, and it's not often true, but for it to be true, we would need to have the IMFs, so the intermolecular forces of the solute and solvent must be identical. So that means that there's no change in enthalpy when we mix them together, right? And so that means that our assumption that the IMFs don't matter holds true because all we're doing is just adding two things that interact in the exact same way. All right, so this is almost never true, but for us in this class, we will always assume ideality. I am not going to ask you about deviations. All right, we're going to assume this to be true. Another way of writing this first bullet here is that delta H of the solution equals 0, right? Because that would mean that delta H of solute plus delta H of the solvent is equal to our delta H mix. Well, negative of that. All right? So lastly, this is not often true in real life, but we will always assume it. In this class. All right, so you don't have to worry about, are we deviating from Raoult's law? But you would deviate for most real solutions, okay? All right. We're going to work through the more complicated Raoult's law situation, and then we'll call it good for today, all right? The more complicated version of Raoult's law is when both components are volatile, okay? So we talked about volatile and non-volatile, and we were just like, that non-volatile stays in there. We don't have to worry about it. We could easily make a solution between two volatile components, all right? So here is the statement. Each component develops a new vapor pressure according to Raoult's law, and the new total vapor pressure is the sum of each component. So let's take that last little bit. The total vapor pressure will be equal to PA plus PB. Okay, that seems straightforward. In our head space, in that gas space, I'm going to have some A's and some B's because now they're both volatile. So my total pressure will just be the sum of those individual partial pressures. Okay, and then to calculate each of these, we use Raoult's law. We say, well, PA is just going to be the mole fraction of A times the vapor pressure of pure A, and PB will be the mole fraction of B times the vapor pressure of pure B. Okay? So the key here when you're looking at problems and you're trying to decide if you're going to have one volatile component or two volatile components is very simple to spot when you get an actual question. So here is a question with two volatile components. And I know that, and it's not a secret. I know it because there are two vapor pressures listed. So if you get a vapor pressure, that thing has got to be volatile because that's the definition of volatile, that it has a measurable vapor pressure. So as soon as you see two of those vapor pressures, that's telling you this is a two volatile component system, okay? So read the question. If you don't get that other one, then you can assume that other thing is non-volatile because we didn't give you a vapor pressure for it. So it had to be non-volatile. It wasn't going out, all right? So in this case, what is the vapor pressure above a mixture of 1 mole benzene and 3 moles of toluene? Okay, let's work this Let's save this for Thursday. We'll start here on Thursday. Hey, how are you?
I have a question.
Hey, what's up?